Hello everyone, welcome to Applied IoT lecture number 10. Hope everybody is doing well. Before going into the part from into the new parts of the lesson, we will first look at what we have learned so far. So we looked into the processing layer or the architecture of IoT system, the basic layers of architecture of the IoT system. Before that, let's refresh our memory on what we have learned so far on this lessons. First, we took an introduction to IoT. Internet of Things describes the network of physical objects. In this case, we define it as things that are embedded sensors, actuators, processing abilities, software, and other technologies for the purpose of connecting and exchanging data with other devices and systems over the internet. So we had our basic understanding of IoT. Then we looked into several IoT devices or examples of several IoT devices that can be classified as IoT, about smart lights, temperature sensors, cameras, motion sensors, smoke detectors, smart plugs, robotic arms, smart locks, so on and so forth, the medical industry, virtual reality, gaming, autonomous driving, weather, health monitoring. So we looked at several examples where sensors and actuators are combined together to make a IoT device. This was followed up by several examples of how information which is generated or the data which is being taken in by the sensors of IoT devices are used by is shared with other IoT devices to carry out different functions. Example number one was a simple demonstration of use of air quality and temperature in the air itself to control the control the thermostat inside a home or a building or in a location. Plus the air quality outside will be considered to switch on or switch off the air purifiers inside that location. So that was a small example of automating a home or a building, so on and so forth. We looked at how several IoT devices network together through the internet and inside the internet itself, working together to resolve a problem or make the process efficient, make the process fast, and so on and so forth, right? So we then looked at how set of data can be used in different domains. We mix and match everything, and then we went into taking an introduction to applied IoT. Applied IoT refers to the practical application of Internet of Things technologies and solutions in real world scenarios across various industries and domains. It involves using IoT devices, connectivity, data analytics, and cloud platforms to solve specific challenges, improve process, enhance decision making, and create value. So ideology the main ideology behind applied IoT is to use IoT devices or to have a IoT platform or IoT system to addressing challenges or resolving problems or improve the existing processes, enhance decision making by the data which is being collected by these devices, and to create value. So we learned about the characteristics of IoT systems, what are there, the connectivity, e-perception, data analytics, or scalability, the properties of those things, security, real-time connectivity, and heterogeneity, edge computing. We looked at all these things. Then we had um, another topic which is now a part of IoT. It is machine-to-machine communication, and how machine-to-machine um, communication is important in this industry, and how IoT helps to enhance that. Of course, machine to machine communication or machine to machine technology is there before even the concept of IoT, but with the current technology and with the enhancements of technology itself, uh, today the line between machine to machine technology and IoT is blurred. So that is something we understood from the examples that we looked at. Different industries, smart grid, transportation, healthcare, so on and so forth. We looked into it, and smart cities. Then we looked at the differences between Internet of Things and machine to machine, scope, data sharing, scalability, connectivity, data analytics, and ecosystem. So basically, um, a legacy system, machine to machine, is a legacy technology which is being replaced or being enhanced by IoT. If somebody asks today to design a system, right, a machine to machine system, it would basic with the requirements and the available technology today, the features that are available, the cloud technology, handling of the servers, applications, the ability to monitor from vibrations of machines, pressure inside pumps, um, temperature inside the room, inside the machine, so on and so forth. All these availability of sensors. A machine to machine system would basically look like a IoT system. Additionally, we talked about OT, which is also something like uh, which is similar to IoT systems and is a concept out there. Uh, we talked about also IIoT, similar in concept, right? So then after that, we went into looking at the market perspective of IoT. The basic outcome of that was that the market perspective in the future is going to be positive. Um, then we looked at value chain, a general understanding of value chain, how value chain works, right? If you take a single company, all these infrastructure, human resource, technology, procurement, and primary activities, which includes inbound logistics, operations, outbound logistics, marketing, and after sales. So all these things, right? If it is a service provider, or if it is a manufacturer of a product, end of the day, right, the value of that product or value of that service is determined by the costs and margin of all these things. So a value chain link would look like something like this, or the value chain uh, of a general company in as a general concept, it would look like this. The investment which is being spent on infrastructure or human resource, technology development, procurement, will be adding value to the end product. Then we talked about end-to-end value chains. In today's world, we have to concentrate more on IoT value chains, which M2M value chains, IoT, IIoT, OT, all these topics look the same as IoT value chains. We talked about in this we talked about devices, sensors, actuators, and we talked about how there are separate, we can look at it in a separately, the value chain. It's all these value chain links from devices, connectivity, service enablement platforms, IoT applications, managed services to the customer is the value chain of creating and maintaining a IoT system to address a specific problem or to improve the processes, right, or to generate information to enhance decision making, so on and so forth. So this would be the value chain for that, to increase automation and so on and so forth. So that means along this value chain there will be um, other value chains will be supporting this, from device manufacturers, sensors, actuators, embedded chip manufacturers to connectivity, ISPs, network service providers, cellular service providers, so on and so forth. Service and enabler platforms include backend programming, right, servers, cloud, so on and so forth, for data storage, management, processing, analytical, computational ability, so on and so forth. Then there we have the application layer, which is normally the layer which interacts with the user, right, including dashboards, notifications, alarms, and so on and so forth. So you have entire software development going on in this application layer. Then we have the management layer, where all these services are being managed, or managing the IoT devices, managing the IoT ecosystem inside the company is being done, which would directly the managed services layer would directly connect with the customer. Either it could be business to business, business to customer or user, depending on the situation. And on that, uh, you will have the ability to sell your product or give your product to the customer as an entire value chain, adding value to the company. So in this we looked at examples. We looked at examples of IoT value chains, from device companies which um, fully or partially engage in building IoT value chains, right? So some of the companies give a set of products or couple of products depending on what you want to get them from. So some are device manufacturers, some are connectivity providers, some are cloud platform providers, application developers, system integrators, data analytics, service providers, and users. So we looked at the chain, value chain, and then we see that in this different value chain you have companies that actually carry out different functions, and we talked about how each company's value chain is contributing value to the entire IoT system value chain. Then we talked about how a simple IoT system is being implemented. We took an example. I think the example was a apparel manufacturing company. So their main goal is to manufacture clothes, right? But if they are looking for a IoT solution, they will contact a IoT service provider, right? The IoT service provider is the one who provides the IoT system from planning to implementation, right? They take care of the IoT products, applications, data management, security, network, so on and so forth, right? Behalf of the customer. This is mainly being done because if you have a company which is specializing on apparel manufacturing, they don't have the knowledge or the engineering capacity to handle the handle IoT technology or IoT system. So it is much more easier, cheaper to get assistance from an IoT service provider. This so as we understand, IoT service providers then would give and maintain, right, implement and maintain a IoT system for the behalf of the customer. So sometimes the IoT service provider would have its own IoT devices, networking applications, so on and so forth. But in other cases, there will be the need of use or need to, like, if the entire value chain of entire IoT value chain is not present in the IoT service providing company, then it have to go and talk to IoT device manufacturers and take their products to build the entire IoT system. We talked about how these IoT device manufacturers then may have to take their hardware from other companies, such as sensors, specific actuators, so on and so forth, to build their product. Additionally, if the IoT device manufacturer is mostly dedicated to building the hardware itself, the software which is needed to communicate or interact with the hardware device should be manufactured by other um, companies with software development value chains, right? It could be then companies that develop applications, they will then seek backend the cloud facilities for their backend, like Azure, AWS, so on and so forth. So AWS, let's say, for example, if you take AWS, then they will be handling the cloud services, which means the hardware and the networking, so on and so forth from the server end. Additionally, if the IoT service provider would need networking capabilities, right? Not in, so let's say the IoT system need to get information from the internet itself, or need to connect to the internet to store data, process data, so on and so forth. Or otherwise, there are multiple factories of this of the customer in several locations inside a country or internationally around the world. If they needed to be connected together, that means there should be networking or ISP facilities should be taken. In such a scenario, we talked about how they will take the services of the ISP, and the ISP would have taking other hardware equipment like switches, core devices, network cabling, so on and so forth from other hardware sources. Um, each and every block that is being drawn here has its own value chain, right? And this entire diagram shows a value chain, a IoT value chain, right? Sometimes the service provider themselves would have all these things inside their company as a product. Sometimes they need to mix and match these things depending on your IoT project. The importance of a IoT service provider is that the IoT service provider will be directly responsible for the customer. The customer would contact if the services go down, or if there are any problems with IoT hardware devices, so on and so forth. The contact point for the customer would on the value chain would be the IoT service provider. It is up to the IoT service provider to look into the problem as quickly as possible, and if this issue needs to be addressed by the application developer of the IoT device, so they need to quickly address that on the behalf of the customer, right? So the customer does not need to either, if it is a business or the customer or the user, whatever, the customer in general does not need to follow through on this, because it is the responsibility of the service provider to check these things, carry out maintenance, and make sure that the IoT system is running healthy, right? This is a concept that is there on IT infrastructure management as well. That is why in here, right, I actually wanted to talk about OT, right? If you take IT, IT infrastructure management is something which is there, and countries like Sri Lanka or India, Bangladesh, countries which has we can say, comparative to Western countries, is which has in respect to the dollar, which has cheap labor, has the opportunity to provide IT service management services to multinational companies around the world, right? There are companies such as T-Systems, Accenture, BT for British Telecom for networking, T-System networking, and other IT infrastructure support, things like that. Even if you take companies that are there in Sri Lanka, WSO2 and those things, they um, they also provide services in maintaining their applications. So they are also a value chain link in IT infrastructure management. Similar to IT infrastructure management, OT infrastructure management is also a thing, right? Companies which have to maintain security systems, alarm monitoring systems, control panels, right, robotic arms, depending on the manufacturer, right? If you are to provide services to a bank, IT services to a bank, it would be IT infrastructure management. But if you are to provide a bank with the infrastructure maintenance of their security system, their bank teller system, the machines they have to count money, these physical devices, it would be a OT system. Let's say if you are to provide infrastructure management to a company which build cars, right? Their financial department, their HR department, their administration department would use IT infrastructure to send emails, messages, carry out online meetings, approve things, ERP systems, and so on and so forth. But if you take the manufacturing line itself to carry out the functioning of robotic arms, cameras, sensors, quality control, painting, so on and so forth, then it would be a OT management system. So that is why I wanted to introduce OT to here, because it this what we talk as machine to machine, IoT, OT, and in some instances as IIoT in the real world is end of the day is IoT value chains. It's similar to IoT value chains and how IoT value chains work. And if you are to start your own startup, if you are to join a company which works on the IoT sector or which works on uh, electronic devices, right, you will now understand the positioning of your particular company against the value chain of a IoT or M2M value chain in the real world. From that, right, we then had a comparison. So we talked about the IoT architecture. When building IoT system, we need to look at the IoT architecture, and we understood that there are four layers when coming in. Generally there are four layers when coming into IoT architecture. Perception layer, which includes the IoT devices or IoT hardware devices, which those IoT hardware devices would include actuators, sensors, actuators, computing processing ability, and power sources, and networking capabilities. Transport layer is all about the perception layer would have networking hardware components, but transport layer is all about the networking of itself. In networking, we talked about two things, or two sections. Number one is the IoT networking, which may use protocols which are dedicated to IoT, is to communicate, or the other layer would be the layer, normal internet itself, where you have where inside the transport layer you find the seven layers of um, networking. Then the processing layer is, of course, cloud server maintenance, uh, basically the back end. Application layer is the front end, where you will have um, uh, the user interaction with the IoT system, whether it is voice commands, a touch screen, keyboard, and you will this looking at the data analytics, right? And those things. As you can understand, we these are pretty similar. The perception layer is the in a value chain are the devices. The transport layer are the connectivity. The processing layer is the service enabler platforms. The application layer is the IoT applications, right, including dashboard, alarm notifications, and so on and so forth. Then maintaining the entire all these four layers is the managed services. After building the IoT device, right, all the R&D testing and everything, you will end up having these devices and you have to maintain them. Similar same in transport layer, processing layer, because you know that if you have learned cloud computing or database management plus maintaining on-premises servers, right, you will understand there is immense amount of administration work and service work that have to be done in maintaining the hardware, to access control, security, and so on and so forth. So that particular part is done. So all these maintenance, similar in application layer as well, is done on managed services. Then of course all these things are given to the customer. So then after that we talked about perception layer and how those things work. We talked about transport layer and how those things work. Then we end up partially talking about the processing layer, and I think we have to start here from data processing. So let's first we will refresh our memory from processing layer and continue from there. Processing layer. In the context of the Internet of Things, the processing layer refers to the layer responsible for data processing, analysis, and decision making within an IoT system. It is the layer where collected data is transformed into meaningful information, insights, and action. The process layer makes the raw data obtained from the perception layer and applies various algorithms, analytics, techniques, and computational methods to extract valuable insights and knowledge. This layer involves tasks such as data filtering, aggregation, correlation, fusion, and advanced analytics. So in this case, right, when we are talking about the processing layer, there are different types of scenarios that we have to look into. One of the points that we talked above is that there are some processing taking place in the perception layer as well, right, where we have edge computing. uh, think think about some different IoT systems and their scenarios. Let's take an example of our one of our best examples was the weather monitoring stations, right? The sensors and the things that we use, but only one weather monitoring IoT device or IoT system in one location will not help to give an overview about the weather in a large area. So there should be couple of them spaced apart at, to cover a vast area in a country, or to cover a country or a region in that way. So the data which is being produced by those IoT devices should be sent through the transport layer through the network to a central processing place, right? In this place is, we would take it as a cloud, right? In that the data will be stored from different IoT devices around that area, giving the temperature, humidity, wind speeds, and so on and so on, those information from those IoT devices. And to get the prediction of the next whether in the next day or next few hours, right, that data have to be collected and averages have to be taken, and they should be compared with existing data models and past data to predict the to give a outcome as a prediction for the next few hours or the next day, and so on and so forth. So in this particular scenario, the data should be collected on the processing layer, where you have servers where data is stored, processed, right? The analytical capabilities are there. Now think of a situation where you have a self-driving car, where you have a lot of sensors which are there, an autonomous car, and the sensors that produced data to find the awareness of the car. So the processing ability, like if you know about Tesla cars, right, we know that Tesla cars are connected to a central server or to the cloud, right, to share information about driving, so that data can be collected, and they can make a better device. But if you think about the real-time data processing which is need to self-driving, image processing, proximity, acceleration, gyroscopes, things like that, uh, it is very clear that even it is very clear a Tesla vehicle would need edge processing rather than sending it to a cloud and taking the information back, right? This is something that we uh, this is something that we um, have to understand, that processing of data, depending on the scenario, the process the processing layer could be in different locations. So in this case, the autonomous driving vehicle would have the processing ability to check the proximity sensors, check the process the images which have been taken and through the cameras, to see if the vehicle can be driven forward or the brakes have to be applied, and so on and so forth, right? So depending on the scenario, data processing uh, changes. So in the processing layer, right, or in the topics that we talk about processing itself, right, um we have the main topic, which is data processing. Data processing. The process layer performs data cleansing, filtering, and transformation to ensure the quality and integrity of the data. It may involve removing outliners, handling missing data, normalizing values, or converting data into appropriate format. So this is what this means is that when you use sensors, right, sometimes due to maybe hardware error, or there's always uh, a small difference in taking readings. It would maybe the values may vary. Maybe there will be an error of 0.25 or something like that. And when that error comes, right, there should be the algorithmic or the processing capability to get the correct value or get the correct averages. So um, this chart below is a good example of that particular scenario, right? So all the sensor manufacturing companies, if this is something that has been taught in IoT, when you go, you will see that they will have their own logs or documentation for each sensor, and those in those documentation they normally show what kind of a error could be there in the reading. It's not a big error, but it is there. So sometimes temperatures, and if you take for example, if you take a temperature sensor, uh, some temperature sensors perform in between, let's say, minus 40 degrees and 120 degrees Celsius, right? So sometimes when it goes above or when it goes closer to the limitations of that sensor, the error rate may go high. So if you dive into the documentation of each sensor, you will see that there is such information given in that. So here you can see that there are these dots which represents data points which is being collected, right? And when collecting data points, we know that there will be background noise or white noise also, if you talk about frequencies and those things, right? So there should be a process to get the raw data and filter it out, do the needed calculations, apply the needed filters to get a proper value. Here you can see there's a upper limit, there's a lower limit which is being defined, right? Anything above that range outliers or variant outliers, which means due to different reasons, it could be from naturally or due to for example, one of the best examples would be um, temperature, or let's say light, right? So normally in your phones you have a light sensor, which you can when you are working with phones outside, automatically the light sensor will detect that there's more light, sunlight, and it will increase the brightness. But if you cover your camera from your hand, you will also see that the if the brightness of the screen will go down automatically. That means that errors could happen due to outside interference, right? So those errors should be filtered out, right? It could be due to material, it could be due to environmental, right? Maybe either sensor receives some dust particles and they are interfering with the reading, so on and so forth. So those things have to be uh, filtered out. um, uh, End of the day, most of these processes will be done within the device itself. So this is mostly edge computing. Again, like the example I gave you before, depending on the particular scenario or particular application of IoT, it depends it depends where the processing of this data takes place. uh, Normally in the perception layer you have edge computing to handle these things, but depending on your requirement, right, that data can be processed in you if the data sets are a lot, and the data sets needed to be run through a lot of filtering and computational algorithms which cannot be handled by small processors. Then then that means cloud platforms should be used, cloud or servers, to help that. So for data analytics, the process layer applies analytics techniques such as statistical analysis, machine learning, data mining, and pattern recognition to discover patterns, trends, and anomalies in the collected data. This enables the identification of meaningful insight, predictions, and actionable information. So, point number one is basically talking about when an IoT device produce a set of readings, right? It is about how to process the data, the raw data which is being collected by the sensor, right? You may if you have gone through lecture number 7, uh, I think you will understand that this is something which is there. Uh, in that lecture you will see that there were some examples, right? There are some set of examples that actually uh, shows how um, different sensors are used to tackle uh, different readings, right? A best example would be the uh, smartwatch, or the smartwatch to read your pulse and for your health monitoring and so on and so forth. That is being done by light sensors. So you have to understand that the computational processes that is needed to be done to take light data, the differences in the light, the differences that they see in that, and put it into equations in such a way that they are able to calculate the heart rate. So in such scenarios, first the sensor data is necessary, and when the sensor data is there, we have to filter it out, make it a clean set of data. That clean set of data have to go through analytical processes, right? Equations or whatever, depending on the thing we are trying to figure out, right? And produce a reasonable value, right? If you take a smartwatch, mostly it would be your heart rate. You can check your temperature depending on the sensors that are there on your smartwatch. If you remember again lecture number 7, the first example we talked about was predictive maintenance. In predictive maintenance, you will see that um, they introduce a IoT ad hoc device to attach to legacy devices such as motors, generators, engines, to see how much vibration is taking place, to see how much heat is produced, to see how much electricity is taken, and those information will be collected by different sensors. And as you can see that those raw data which is being collected from the sensors have to be right, it would be something like this. There will be errors from the sensors themselves. Let's say they are trying to monitor the heat of that machine, right? It would be something like this depending on the situation, but maybe small differences due to the material or due to the surface or somebody moving nearby the machine or things like that, right, interferes with the sensor and error readings may come around. So those things have to be filtered out and a purified number have to be given. When that happens, right, they will then put through pre-known values of uh, either material science or pre-known values which right pre-known pre-existing data which was collected maybe months ago, and see that if there are some differences in vibration and heat in of the machine itself, right? And if there are significant differences, then an alert can be created that pre-maintenance is needed. Somebody have to check this machine before it breaks down, because the health of the machine is being deteriorated, right? So those information can be shown. So in data analytics, that is what happened, right? When the sensor data is processed and purified, that data is used in computational, those are computational scenarios, right? There would be equations or there would be a past set of data to be compared, things like that, right? And from that a set of data can be given to show that if the health of the device is working correctly or not. Decision making based on the analyzed data, right? So when that reading which is taken, let's say today, is compared with past readings of maybe 1 month, right? When that equations are done, when the charts are drawn, the visual representation, right? We are talking about the visual representation. So when the visual representation is done, right, based on the analyzed data, the process layer makes informed decisions or generates recommendations. The decision can be used to trigger actions, automate processes, optimize resource allocation, or enhance operational efficiency. Yes. So that particular data, that data would be either shown to a human being where they can see that, oh yes, the temperature has gone above, has been increasing steadily throughout this month, and we need to maintain this machine, run some tests, so we need to take it out for maybe cleanup or things like that. If you take a smart electricity grid, right, I think we have talked about this scenario as well. If you have a smart electricity grid, and when you can take the weather IoT readings, right, from IoT, from temperature or depending temperature, wind, so and so, and we know that when in a day where temperature goes very high, there will be more air conditioning, fans, and so on and so forth will be used, so the consumption of electricity would go high, right? So in that scenario, either automated processors, if the process of maybe releasing or usage of water in a hydropower plant, or you inputting more coal into the furnaces of a thermal power plant, right? uh, or activating more wind turbines to increase the electricity production. So these things can be either automatically triggered, or humans can look at the data, right, and look at the parameters which are there, compare them and make a decision. Then there's real-time processing. In many IoT applications, real-time or near real-time processing is crucial. Yes, we talked about this. If it could be from weather conditions to self-driving vehicles, right? Most of the time, if you have a patient in a hospital, again, real-time data should be given. The process layer handle the time-sensitive data, enabling immediate responses, alerts, and actions to be taken based on the analyzed information. Yes. So depending on the requirements you have of your IoT devices or your IoT system, let's say if it is a hospital, right? If you get the data from the sensors, that data must be quickly processed, and data analytics should be done very quickly, and then in real time, right, in milliseconds, that information should appear in front of either the nurse or doctors for them to analyze. So in that particular scenario, a set of edge computing would take place, or computational servers inside, maybe inside the hospital themselves, would carry out these functions, right? So so the thing that is needed to be remembered, that the processing layer, uh, you may see it in cloud computing level. You will also see a part of it in edge computing or inside the machine itself. You will see it as on-premises or servers which are being dedicated to the company or the IoT system itself. So depending on the requirement, right, if it is real-time processing, right, the computational power and the amount of resources needed should be increased, and so on and so forth. So that is when you are designing a IoT system, it depends on it, but basically, right, there is this processes taking place normally in the processing layer. If you have bulk processing or high computational processing, a set of or edge computing happens in the perception layer as well. Those are also processors, but that is something I think it's better to remember, because in a time when you apply your IoT application, right, maybe let's say you have to have a camera which have the processing ability to do image recognition in the device itself, or a camera which have to send its image data to a server centralized or the cloud to do the image recognition, run the image recognition process. So in that particular case, depending on the application, right, you can choose your device and your processing ability. So if you take data analytics, right, you have your parameters, right, you first you will find your storage, right? Your data collection, your past data, right? Even if you have real-time data, for the real-time data to make sense, you have to have past data values, data points, right? Today you will read the temperature of something, but you don't know whether the temperature is high or low, because you don't have any data points to read from the past. So that means it is quite essential to have to store this data, and to store in that much amount of data, especially in IoT, large amount of data is created. The processing layer would come into play definitely. To store large quantities of data, the processing layer, especially technologies such as cloud technology, will be used tremendously. And to process such amount of data from, let's say, 500 devices, again, cloud technology is a good way of allocating resources, right? So data will be filtered, analyzed, and it will be shown in a visual way for the human to make the decision, right? If automation takes place, for example, in data analytics, right, in that stage, it automatically, right, code will be written in a way that automatically that functions would actions would take place. So more the automation, the human touch would go away. But end of the day, to see that everything is working correctly, right, the visual representation should be given to the human being. So up to data analytics, right, is handled by processing layer. The visual representation and the interaction between the human and the IoT systems take place in the application layer. The application layer in IoT encompasses a wide range of applications spanning various domains such as healthcare, smart homes, industrial automation, transportation, agriculture, and more. It involves software application platforms and user interfaces that enables users to interact with the IoT system, visualize data, control devices, and access IoT services. So yes, we know this. You have for smart homes, you have your Google Nest, or you have Alexa to talk to and give commands, right? Voice recognition systems. Then if you have industrial scale applications, you have your control systems, web applications, so on and so forth, right? And you have if you have a smart device or a smart home, you would basically operate everything through application as well. So these are the methods of interacting with the IoT system, right? Basically the application layer does that, right? It would be a visual, it would be in a let's say in a electricity production power plant, right? Maybe the sensors, right, depending on the notifications they have to give, it would be either light bulbs, or in the screen you will see a chart to show that how much electricity is being produced, or alerts being created that the machines would need maintenance, so on and so forth. So we will talk about some subcategories of application layer. So user interface. These interfaces can be web-based dashboards, mobile applications, or specialized applications designed to specific IoT use cases. They provide users with the means to interact with the IoT system, monitoring device status, configure settings, and access relevant information. So basically, right now we are talking about, in the application layer, we are mostly talking about application development and mostly about front end, right? In the processing layer, we talk about the back-end processes which takes place: storage of data, data security, processing, analyzing, filtering, running through algorithms, using cloud, using server systems, so on and so forth, right? In the transport layer, we mostly look at the networking which holds everything together, and in the perception layer, we look at the IoT devices themselves. So I think application layer is easier to understand because it is something we normally interact on daily basis. IoT services and applications, these are specific services or applications built on top of the IoT infrastructure to cater to the needs of the user or business. Example including remote monitoring and controls, or predictive maintenance, energy maintenance management, asset tracking, and many others. So these examples, again, if you have gone through lecture number 7, I think you have gone through these examples very well, right? You know where to find them, what are the topics to research to find uh, these things. Right now you would have an understanding of what we are talking about, right? We talked about predictive maintenance, right? What is being shown, how these things are being used, how IoT devices are being used, so on and so forth. Then the third one is integration with external systems. The application layer often involves integration with external systems such as enterprise resource planning, ERP systems, customer relationship management, CRM systems, or cloud platforms. This integration enables data exchanges, interoperability, and enhanced functionality. So a good example of this, is logistics. Pick Me or Uber, right? In that you have the ability to see your vehicle when it is booked, right, coming towards you, how long will it take, right? And you can share your journey details with anybody you need, right? Your location, where you are going, how long will it take for you to, so how these, when you think about it, how this information is generated, right? uh, Either, so we know that the device here which is being used is smartphones, your smartphone and the smartphone which is being used by the Uber driver or the Pick Me driver, right? So so that smartphone will triangulate your location from cellular data, or or using GPS data, right? From that, not only your position, your vehicle's position as well, the vehicle you ordered through. So then they will make calculations in real time. How long will it take, right? For your journey, how long will it take to come and pick you up, or if you order food from those things, right, how long will it take to be picked up and delivered, so on and so forth, all that. So to generate that data, cellular, the information which is being created from cellular phones are used. The IoT device here is the cellular phone. So, but if you think about, if you are ordering something from Amazon, if you are ordering something from um, uh, maybe from online retailers, you will see that your product is being delivered from place to place. Maybe it is coming from abroad, but sometimes in some applications exact location can be found out. How is that done? If you remember, again I will take you back to lecture number 7. There was an example about logistical tracking, a IoT device, ad hoc device you can add to your vehicle, right, logistical vehicle, where that information can be shared with the customer. So when you have a ERP system or a CRM system in your company, you can integrate that with data which is provided by IoT systems such as logistical tracking, either through RFID or NFC, geolocation, so on and so forth, right? And that information can be given to the customer through your CRM system or ERP systems. Why this is important? Not only for local users, right? Not only for local users, like individual users. If you think international trade itself, right, there are companies which transport goods which are immensely valuable. It could be precious minerals, like if or vehicles which needed to be transported through ships. It could be things like diamond, gold, and things like that. It could be right, 10,000 iPhones through inside a container, going through things like that. So those things have to be tracked very correctly, and if it would be much better if the if to see if those devices are being transported with much greater care, where there will be no extra vibrations or extra heat for those devices, so that the health of those devices can be maintained. So when coming into industrial applications, IoT systems that support logistics are very important, right? They are very important mainly because this would help to safely send products to the end user. Either it could be business to business or through business to customer. So now you can see why these integrations are very important. So other one is final point would be data visualization and reporting. The application layer may include tools and components for visualization IoT data through graphs, charts, and reports. This helps users gain insight from the collected data and make informed decisions. Yes, so the same scenario we are talking about. This is a good example of what we are right now talking about. You can see the amount of humidity, you can see the temperatures being showed, right? You can from this you will like this is an example representation, but this representation is what maybe a IoT control panel may look like. If the IoT system is looking at vibrations, right, these values will be changed from temperature to either showing the vibrations, right, the changes in vibrations, so on and so. Here you will see that this is measuring temperature, right, and that temperature can be compared throughout, right, dates and everything. So there will be filters to check from there will be filters to check past data and to compare past data with the current data to see if there are any problems, things like that. right? This is just a small example of a control panel. um, so we have main design principles and its capabilities. We can, so most of these things, right, are the properties of IoT devices. Now in this first, we have talked about the architectural nature, right, the main four layers of IoT. When you are applying IoT solution, right, for either automation, making the process better, for decision making, or to solve a problem, you have to, if if you are trying to manage the services of providing IoT solutions, then you should have an idea and a plan for all these four layers, right? That is how the IoT value chain completes itself. I think now you have an understanding of how this is working, right? If you want to have a value IoT value chain, if you want to manage IoT value chain, if you want to build a IoT value chain, right? If you want to manage the services, you have to have, so that means you are going to give a IoT application, a IoT system as a product to the customer. It could be business to business, it could be business to customer, or to the user, right? So from here only you can go to this step, but to come up to here, you have to build you have to have and have the capability to build the perception layer, then the transport layer, then the processing layer, and the application layer. Not only build, and to maintain, right? So next, from that point, right, now I think you understand the value chain. Now you understand what are the layers that are there and how it's going to be, right, in a general IoT application, right? It's not only about the device. When mostly we talk about IoT, it's about the device. But if we are to apply IoT, if we are to create IoT system, it's all about the device, networking, cloud, and interaction with the user, which would be the application. Then now we can move to the next topic, main design principles and its capabilities of IoT systems. The first point of design principles or capabilities of IoT systems is scalability. So if you remember the characteristics of IoT or IoT systems, when we talked about, scalability is one of the main characteristics that it has, right? So it is an important feature, right? If you are building a IoT system, the IoT system should have the capability to add more devices into the existing IoT system, right? For example, let's take our favorite example. Our favorite example is weather monitoring IoT devices, right? If we want to take more accurate weather readings, the amount of IoT devices to monitor the weather in a certain area should be increased. Or if we want to increase the area that we are monitoring, again we have to increase the amount of devices. It is the same platform or same control center that we are using, but same types of devices that we are using, but we have to increase the number of it, so increase the volume of it. So when we are when we talk about the architecture, right, this these are the 4 layers. In these 4 layers there are specific things to support a IoT ecosystem or a IoT system. And this architecture, this block which contains 4 layers, all these 4 layers should have all these 4 layers should have these design principles and capabilities. When we talk about design principles and capabilities, those 4 layers should have these topics. So first one is scalability. IoT systems should be designed to handle large number of devices and accommodate future growth. They should be able to scale seamlessly as the number of connected devices and data volume increases. Here you can see that the number of connected devices, so that means this, when you go through the architecture, it should have the perception layer should have the capability of adding more devices in. If we are using a security system and if you want to increase the area of that particular security system, then the number of the ability to increase the number of cameras should be there. Then there is another statement saying, and connected devices and data volume increases. The data, that means if we are all these sensors, more than the actuators, the sensors create data. And if we are to increase the sensors in the perception layer, the amount of data being produced will be also increased. What that means is, first, each IoT device is networked. So the transport layer should have to have the ability to network them and handle the extra load of data which is being transmitted by the new devices. The processing layer should have the ability to store and process large quantities of data as well. So when this whole when talking about scalability, the entire architecture, all 4 layers have to have the ability to scale up, expand from the existing system. So so we can look at different aspects of things which are which happens when increasing or having the property of scaling up, right? So when talking about scalability, we will start with device management, which is from the perception layer. IoT systems should be designed efficiently, should be designed to efficiently manage a large number of devices. This includes mechanisms for device registration, provisioning, configuration, and software updates. Scalable device management platforms and protocols help streamline the onboarding and management of devices. So you can see that there are some important facts which are in here, right? If you take device management in the perception layer, They talk about the ability to increase the number of devices in the perception layer. But what does it mean by increasing the number? It's about registration, provisioning, configuration, and software updates also. So, before talking about IoT, I want to talk about IT. If we, if you have learned about IT, infrastructure management, right? And if you see Microsoft products with Azure, which they have provided, you will see that they have a set of software, so set of categories to facilitate device management. When Microsoft says device management, it is mostly laptops and desktops, right? They have so they have in their Azure portal, as well as in their right, EUC designs or end user communication designs, right? They have their device registration. There are knowledge management portals like ServiceNow and so on to keep records of these registered devices. So provisioning, same. Configuration here, we can say, for example, different companies may need different capabilities from hardware components, right? So for example, if you have a security system, some might say we want the cameras to shoot in HD. Some might say we don't need cameras to shoot in HD, but we would need the ability for night vision. So there are different configurations, different options. Either they can be triggered from software updates, or they needed to be updated through physical updates itself, right? So that is also option. Then again, of course, every hardware device needs software to function, and updating that software is also there. For here, if you take the Microsoft example, if you go back to Microsoft in IT, ITSM or IT service management, you will see SSCM tool and Intune tool is there to push updates, right? In your if you in your laptop, you will get updates. It could be to increase the efficiency of the laptop itself, to fix bugs, and of course security patches. So similarly, when managing devices, right, that platform should be there, because these are also hardware devices which are being networked to a system, and they might have bugs, they might have functionality issues, they might have security loopholes, right, security gaps which is needed to be covered through software updates. So the app, if you are a person, or if you are a company in this value chain which makes devices, right, we talked about this, right, a company that makes devices have to make application for that device itself, right? And in that there's the back end as well. So they should have, the application and the backend should have the ability to push updates, security updates, or whatever the updates to the hardware device itself, right? um, and registration is also a security feature, right? If you are saying, okay, we are going to use smoke detectors, or mics around a building for security purposes or to monitor the sound pollution or things like that, right? If there are 150 devices, right, we we have to check whether all the 150 devices are registered with our IoT system. If we find if there are 151 devices, that means somebody has tried to hack into the system by adding their own hardware device, which should be stopped. So that's why the registration and provisioning these things are important, right? So when you sell or when you produce a IoT device, along with that, these capabilities should be also there. Scalable device management platforms and protocols help streamline the onboarding and management of the devices at scale, right? This is what it means. So if we can give them the control panels and control systems, some admin rights for registering those devices, registering those devices to the network, registering those devices in the system, so that data which is being produced by those systems can be trusted. And when if we are to uh, monitor each device and to maybe provide, if it is monthly billing as a service, right, to keep track of those things, right, to identify each device. So think about it, if you have a control panel like this, right, this is another scenario why we need to have registration and everything in so let's say here it shows the health of the devices. It shows a device in such as a control panel, they can see okay, health is good for all the maybe lot of devices. One would have a error, it would be a hardware failure, it would be a network connection issue, something like that, but it has generated the error in the system. But if we haven't registered that device properly, let's say in a 50-story building, one smoke alarm is not it's not working properly and we have an alert. If that device is not registered with the proper information, including the device unique name, location, the floor number, so on and so forth, it would be very hard to locate that device in a large scale building. And when we talk about IoT, especially in industrial level, we talk about large scales of IoT, and that is why in device management all these services should be there. So when more the capacity increases, we will have records, we will have the ability to update software, we will have the ability to track these devices, create trust relationships, and so on and so forth, right? So in scalability, when talking about scalability, device management is one. Then network architecture. The underlying network architecture should be designed to support a high volume of data traffic and device connectivity. Scalable network technologies such as mesh networks, distributed architecture, and hierarchical structures help distribute the load and provide robust connectivity for a large number of devices. So if anybody who has studied networking, right, would understand that when you build a network, depending on the capacity of each maybe depending on the number of switches, the bandwidth, so on and so forth, right, the amount of IP addresses that can be used, there will be limitations for the amount of devices that can be used in that particular network. But if we are to add more devices to the perception layer, all those devices should be networked. That means the bandwidth should be either increased, either there should be load balancers. So mesh networks would help in such a way. If there are traffic taking over one pathway, another pathway can be used. Distributed architecture is similar, right? Hierarchical structures would help with distribution switches, load balancing, and of course redundancies would be also needed, right? Things like that. And whatever the architecture that we use for the design, it should have the ability to add one more device when needed, add one more path when needed, add if you take the usage of IP addresses, again it should have the ability to add more IP addresses, so on and so forth. Similar to if we talked about the architecture, so the entire architecture model, all these four layers should have the ability to expand alongside the requirements. Next is the data processing and analytics. As number of connected devices increases, so does the volume of data generated. IoT systems should incorporate scalable data processing and analytical mechanisms. This can involve distributed computing, edge computing, and big data technologies to efficiently handle and analyze the large influx of data. Yes, if we are using 50 devices, and if we add another 50 devices into the same system, that means we have increased the number of that particular IoT system 2 times. That means we need the processing power to analyze that data 2 times. So that's why we talk about in the perception layer there would be some edge computing that would help us, right? We can concentrate from that. Then we can also concentrate the amount of resources that are allocated for processing, including increasing the CPU, the number of CPUs which are dedicated for this, right? Increasing the RAM of the services, so on and so forth, to handle large amounts of data. Think about a scenario where you have to have real-time data when coming into weather, security systems, temperature, things like that. You have to process those data in real time, so that it is abundantly clear that we have to use either increase the number of hardwares to process this amount of data, or we have to use algorithmic techniques to handle large quantities of data. If here anybody learns about big data technologies, I think that is also helpful when looking into these things. But here again, we are not going into heavy technical portions. We are going through theoretical parts, right? If we are to step into the IoT field, IoT world, right, you may know where to look. From this lecture, what we expect is you will understand where to look when designing this, right? If now we are talking about perception layer, transport layer, processing layer, applications, so if you go for each is a different subject and a different we can therefore this lecture will never finish. So that's why we are not going into the technical part of things. We are looking in the theoretical overhead of things, how we can apply IoT, right? If you by now you know, okay, if we are to build a architecture or if we of a IoT system, we know that there are 4 layers. We know what the 4 layers contains, right? We know what are IoT devices, what are sensors, what are actuators. Okay, what this is the problem, how to find a IoT solution. We know the transport layer. We have, so we can talk to network engineers to design these things. Data processing, storage, backend, front end, software development, so on and so forth, right? So this is something that to give an overview of what to look for in IoT systems, right? So data processing, similar as I told before, right? Similar to uh, perception and network layer, these data processing should also increase. So not only data processing, the cloud infrastructure, right? There are many features that is given by cloud. If we are to use cloud infrastructure, then the resources which is there on the cloud should be increased accordingly. Cloud computing platforms provide scalability by offering flexible and scalable resources to handle the processing and storage requirements of IoT systems. Leveraging cloud infrastructure allows for elastic scaling, on demand provisioning of resources, and the ability to handle dynamic workloads. Yes. So this is something why cloud and IoT go very close together. If you learned about cloud computing, if you learned about Azure, AWS, Google Cloud, you will understand that they will have set of packages. These packages would give options in scaling up or scaling down the amount of resources that we can use, the memory that we can use, the processing power that we can use, right? The storage capacity that we can allocate, so on and so forth. The billing of those services will also happen according to the use of resources, right? Everything about the servers, taking backups, security, so on and so forth will be handled by the service provider. That's why a cloud is easy to handle, because you don't need to have your own server farm to run these systems. um, it is very good for a expanding company where you would need scalability. And here in IoT, scalability is a key characteristic, right? It's a key characteristic of IoT system. So for the backend storage of data, processing, increasing the processing power, so on and so forth, we can leverage cloud infrastructure, which is being provided by different cloud service companies. We can leverage that to increase the capabilities of the processing layer, which is uh, which is a good thing, because before cloud technology itself, right, if we are to increase the processing layer, we should have our own servers. We have to maintain those servers, right, do regular checks, updates, so on and so forth. That whole infrastructure today is moved to as a service to some, and some companies provide them. So we don't need to worry about our data security, we don't need to worry about outages, we do things like that as well, right? um, of course we need to manage them. When you're coming into data security and everything, we have to manage them by introducing options. And you know, if you take Azure as an example, you have everything on your Azure portal to handle these things. So uh, uh, again, cloud services is by nature, cloud infrastructure is scalable. So to help the scalability characteristics of IoT, we can leverage cloud infrastructure, right? That is one of the main point. Then message brokering and middleware. IoT systems often involve message brokering or middleware components that facilitate communication between devices and applications. Scalable message brokering systems ensure efficient routing, querying, and delivery of messages, even with high volume of concurrent communications. Yes, message brokering and middleware. So again, this is a point that we talked about. uh, when you have hardware components which produce continuous data, right? When you have a sensor that when you activate that sensor, it will continuously produce data. To handle that data, to send that data, right, to communicate with the transport layer, to turn that data into a format um where the application or the user to understand, or to the machines that this data is stored to understand, right? You would need middleware. And that particular part, right, when we talk about middleware, here in when you are creating the hardware device, you have to make sure that you make the middleware that which is necessary for the hardware device as well. This can be achieved by application developers, right, either in-house or externally, because uh, software is something that is not physical, so we are trying to create non-physical uh, things which we call data from a hardware device, right? So we know that yes, we use when we use a web browser, right, when we use chat, video call, email, those things, right, and when we use internal hardware um, of a device. In this case, it could be a laptop, it could be a smartphone, or a tablet PC, right? Your fingerprint sensor, your face recognition, right, so on and so forth. These, when you get the data, right, they should be turned into a format where the device and the rest of the hardware could understand. Then again, they have to be converted um, into a format where the human being could understand, right? So for that, we need it these signals which is being produced, right, should be sent as messages to uh, to the to the devices either to store them, right? Like if we are to take the again the weather example, right, the temperature, edge computing will produce data about the temperature, but that to happen that, right, message brokering middleware components that facilitate communication between devices and application, right, should also be there. And the scalability of that as well, how the um, how when, as we talked about earlier, right, when devices increase, the network architecture, the processing ability, the storage, and of course the middleware also need the capability to handle the increasing amount of messages that is being sent, right? Then horizontal scaling. Horizontal scaling involves adding more resources, such as server or nodes, to distribute the workload and handle increased demand. By designing IoT systems with a modular and distributed architecture, individual components can be scaled horizontally to accommodate more devices, data, and interactions. So, horizontal scaling means that the again we talked about network architecture needing to increase, the amount of processing power needing to increase, cloud infrastructure things needing to increase, right? We talked about middleware having the ability to handle the increasing amount of devices and the data which is being produced and broadcasted from there. So horizontal scaling is involves adding more resources such as servers or nodes to distribute the workload and handle increasing demand, right? If so again, this is similar to increasing, if we are to use cloud resources, it is similar to increasing cloud data. Now if you have the network architecture itself, right, uh, you could you could have in a way that you can add components like Lego, right? if if I were to say, okay, you have one two sorry, let's say if you have to say you have a set of devices, right? Just right, let's keep it like this just for uh, example basis, right? And these are networked, right? Now these could be IoT devices, these could be servers, uh, these could be network switches, so on and so forth, right? Let's say that this is the simple introduction to it, right? But if we are to introduce another four devices to the system, we will just say we are going to introduce another four devices, right? Let's say this is 100 IoT devices, 100 IoT, right? This is 100 IoT devices. We will add another 100 IoT devices here, right? So this will be the network infrastructure that needs to handle the 100 IoT devices. This would represent the server capacity, the processing capacity, the storage capacity, everything, right? If we want to add this, the entire thing, we have to add the new networking and everything to this as well, right? If we are to had these 100 IoT devices here, right? Think about the mesh network that is needed to be created. It would be a little bit uh, hectic. So rather than that, we know that okay, there is a functioning system over here, right? We can build it like Lego means, okay, we can build a separate system like this with mesh and everything. These 100 is working together, but right, let's say okay, they are server to server, this is being connected, like this. If we want to if we want to add another 100, we will just replicate this again. We will replicate another one again, right? So it's like putting Lego blocks on top of each other, right? uh, so similar to the number of devices, the number of servers or nodes, or the distributed the workload that is being handled and demand is also being increased, right? If we add these 100 devices just here, these either, let's say this is a core switch device which handles everything, and the networking, the servers and everything will run out of power. So it's like building blocks, right? If you have 100, you need this much resources, networking, perception. So if you have this 100 devices in the perception layer, you need this much of networking, this much of processing, and so on and so forth, right? If you want to increase by 100, you add a similar block to the existing system, including in processing ability and so on and so forth. So this is what is meant by horizontal scaling, right? Rather than trying to put all the stress on one block, right, vertically, we are just expanding in similar components. Interoperability and standards. So here, standardization and adherence to interoperability protocols and frameworks enables seamless integration of devices and systems from different vendors, with facilities scalability by ensuring this facilitates scalability by ensuring compatibility and easy integration of new devices and technologies into the existing IoT ecosystem. I think you may remember the examples and things that we were talking about. Hopefully, we were talking about interoperability as a characteristic of IoT devices, right? um, the ability in scalability, we talked about this a little bit, right? What we were trying to say here, or what are we trying to say here is that if you have a standardization of code standard, right? If you have open source architecture for the code, for best example, Alexa, right? Third party device manufacturers can create IoT devices to interact with Alexa. Alexa would work as the command center, but other third parties have the ability to make their devices compatible with Alexa. So that is the interoperability, and standards are there for that, right? If we are to connect to the internet, we should follow standards, network standards, right? We Zigbee, Sigfox or things like that doesn't have the standardization to connect to Wi-Fi. So that means in between there should be something to translate that particular protocols and data packets from that particular protocol to another one. So standardization is very important for scalability. If we buy a set of devices from vendor A, and maybe another 7 devices from vendor B, because the vendor A doesn't have them anymore in stock, right? And if those products are not compatible, let's say either the network connectivity, the network protocols, and the network they use, right? Let's say one use Bluetooth, the other one use Wi-Fi. So if there are issues in standards, there will be issues in communicating. Issues in standard in creation of data, right? Especially the especially the way that we the set of data which is being generated on top of because they needed to be stored, and they needed to be in one single uniform format, things like that. So there should be a standardization of uh, standardization of the ecosystem itself, the technologies and so on and so forth, right? When we talk about interoperability and standards, even if you have a like think about a security, this is a very simple example. Think about a security system, and what will happen if the cabling of a set of cameras is, let's say, USB C connectivity, and another 5 cameras are looking for Ethernet connection. Now you can see that there will be an issue in building that system, adding the new cameras, right? So if you have learned about DevOps, right? DevOps is also there in the software world to handle this standardization and interoperability. So not only in the hardware world, the software world is also facing the same issue. Next is monitoring and management. Scalable IoT systems require efficient monitoring and management capabilities. Centralized or distributed management platforms should be in a place to monitor device health, network performance, data flows, and system resources. These tools enable proactive maintenance, troubleshooting, and optimization to ensure smooth operations as system scales. Yes, so we talked about it a little bit before as well in an example where you have your dashboards to if you you have your dashboards to see whether devices are working correctly or not, right? You have to have the ability to see if there are over usage of processing power, if devices are going into hung state, or their devices are frozen and they needed to be restarted, or they are having power outage issues, things like that. So everything have to be monitored. So there should be, this is a we are talking about the application layer, so that means the application layer should have the ability to expand alongside rest of the 3 layers as well, to give enough data to the user or to the customer, right? So in scalability, all these points are very important, right? So again, most of these things are theoretical things that we look into, right? But when, right, we are not going to say, okay, we are going to use this code and we are going to use this hardware system. If we are going to use this right Ethernet connection, or we are going to use ports with USB-C only, what about USB-A, or things like that. What we are trying to learn from applied IoT is that if we are to give a IoT solution, if we are to build a IoT system, how does the architecture look like? What are the main points of the architecture which we talked about? Then we are looking at the design or the capabilities of IoT system, design principles or capabilities of IoT systems. If we are to build a product and show it to the market, for the market to accept our product, for people to buy our product, that product should have these abilities on it. So scalability is one of it. Scalability can be talked in different topics throughout the 4 layers of the IoT architecture, right? Then it's interoperability. So to talk about interoperability, we have to wait till the next lecture, because now we have reached close to our 2 hour mark. So we can stop the lecture for today, right? So as you can understand, what we are trying to do here is we talked about value chains, right? When we talked about value chains, we talked about where and which points that value can be created in the sector of IoT or the IoT domain. When creating IoT system, which places, which topics can be addressed, and where value can be created. Value can be created on hardware level, service providing level, device manufacturing level, application backend, and networking levels, right? So this is what we learned. Then we learned about the architecture which creates the value chain, right? And the 4 layers of that. Then what we are now learning is, when you create the architecture, what are the properties that are going to be, right? What are the properties that defines a IoT system, the capabilities of IoT system, and the design principles of a IoT system. When you in applied IoT, what we are mainly focusing on is, when designing a IoT system, not just a IoT device, but a system. What are the components? What are the value chain looks like, right? And okay, we have a value chain like this. So what are the layers that makes the architecture? We looked at that, right? Now we are breaking down on the architecture into design principles or properties that are there in IoT systems. So we talked about scalability. Now we have to go for interoperability. Not interoperability, not only in perception layer. We have to talk about interoperability in networking or transport layer, processing layer, and application layer as well, right? Most of this is, right, theory, breakdown of these things. Then we talk about security in all 3 layers. Then we talk about reliability, right, reliance on a system, what is needed. Then data management, right? Then privacy. Then energy efficiency, we talk about those, real time and latency, and those things. Most of them are theoretically. We are looking at these principles in depth. We are looking at them in depth, and we are looking at them on a theoretical level, right? We are not looking at it in a practical level. We are not going to look at it in practical application. We are looking at it in a theoretical level. So we can stop the lecture for today, right? As you can see, there are a lot of notes that is needed to be covered in the next lecture, right? To talk about the design principles, the capabilities of IoT, regarding all these four layers. I would add one more point before ending this lecture. That is that though we talk about IoT systems, especially IoT systems that is being used in industrial scale, where we call it M2M, IoT, IIoT, or OT, or whatever the new trendy name that will be there, right? The the main thing that you have to understand is the more we go into this, right, you will understand it's not only about IoT. IoT system is about networking, is about, it's about cloud computing, and it's about application. So there's, we are talking about back end, front end, that is, that means software development life cycle itself. We are talking about data management, we are talking about security, we are talking about transport layer. So the last three layers, except for perception layer, it is, we are mainly talking about IT infrastructure. We are talking about IT, we are talking about software, we are talking about data management, big data, things like that, and analytics, so on and so forth, processing power, cloud computing, so on and so forth. So that means in IoT we share properties with the IT sector, right? So if you are to step into the IT sector, if you are to create a software company, if you are to join a software company, it is very easy to create a perception layer, because you will be already handling the transport layer, processing layer, and the application layer if you are in an IT infrastructure company. That is why I, with my personal experience I wanted to introduce this small section for you, which is not in the syllabus, OT, right? In IT you will see cloud computing, you will see server management, you will see devices, you will see end user management, you will see databases, security, network security, right, so on and so forth. In OT, the difference between IT and OT is that the hardware devices or the perception layer is there, right? It's not only mobile phones, laptops, and desktops. It's about security cameras, sensors, meters, robotic arms, so forth, on and so forth. So when we talk about machine to machine, when we talk about IoT, right, that is the main difference. That's why you see that there is a place where these everything meets. If you take cloud computing, IT and OT have cloud computing with it, they have networking with it, right? So uh, right, so we are traveling in a direction where we not only we are talking about things that are applicable for IoT systems, but for IT infrastructure as well. But one of the but have to remember that, right? We talked about the value chains. We talked about what are the places where we can find value, build things to add value to the IoT value chain. We are talking about the architecture of that IoT system where the value chain lies, right? If you build in the entire architecture, now we are looking at properties of that IoT system, right? This architecture is for a IoT system. That architecture has four layers. We talked about it. Now we are looking at what are the capabilities or design principles that we consider when designing the IoT system, or when designing those four layers. Okay, so I think we have covered for 2 hours. I will see you in the next lecture. Thank you everyone. Have a great day.